Starten, Aufnahme starten.
Bist du hier durch? Hallo.
Was machst du heute denn? Denn was? Spielpicks. Genau. Bin ich mehr oder weniger durch Zufall reingestolpert.
Jetzt dein Laptop oder irgendwas draußen oder soll ich Handy nehmen? Hier schreiben, falls das kaputt geht.
Ich lasse den Laptop laufen.
Ich wollte dich noch was fragen. Was ist denn mit unserem Paper? Gibt es jetzt noch was zu tun, wo wir von allen okay haben?
Nee. Ich dachte, du hättest schon eingereicht.
Hä?
Ich dachte, du hättest schon eingereicht, nachdem ich geschrieben habe, dass du...
Da ist die Verwirrung. Okay.
Aha. Immer der erste Autor.
Du hast dich als kommunizierenden Autor eingetragen, da habe ich gedacht, okay, das heißt, ich soll es einfach einreichen. Oder sollen wir es zusammen schnell machen, morgen in deiner Sprechstunde?
Morgen in der Sprechstunde. Morgen habe ich keine Sprechstunde.
Moment.
Ach so, die ich hier verbringe. Das kann man machen, genau.
Okay, dann kann ich einfach morgen
Das müsste eigentlich ruckzuck gehen.
Ja, ist alles fertig. Ich habe jetzt auch einen GitHub-Link eingefügt für den Code.
Ja.
Das ist das Einfachste, dann müssen wir nicht
Ich habe mich einfach als Corresponding-Autor eingetragen, weil das ja eine E-Mail-Adresse sein sollte, die dann in dem Paper steht und die dann auch lange Zeit verfügbar bleibt und sowas.
Ich dachte, wir hätten das so ausgemacht, dann haben wir uns nicht missverstanden. Gut, dass ich nachgefragt habe.
Sehr gut. Ich dachte, es wäre längst unterwegs. Ne?
Ja, du hast es mir gesagt und dachte ich, okay, das heißt ja, dann müssen wir so hochlegen wollen.
Dann läuft das ja.
Okay, dann machen wir das mal.
Ich weiß nicht, der hat das Ding eine Mail bekommen, weil er so eigentlich ist.
You're looking into the past. Da gibt es keinen Weg mehr raus. Ja.
Kein Weg mehr raus oder kein Weg mehr rein?
Alex, könntest du mal mit dem Handy schauen, bitte, weil irgendwas funktioniert hier nicht ordentlich. Also, er lädt da rum. Ohreule, genau. Eigentlich sollte man Eule noch mit OI schreiben.
Wahrscheinlich ist es Rom.
Willkommen im Live-Chat. Gut, jetzt lassen wir mal, was da los ist.
Ja. Ich habe Angst, dass Ethereum nicht funktioniert und die mobilen Daten hier im Gebäude auch nicht funktionieren.
Aha. Aber der Computer hängt ja, glaube ich, übers Kabel dran.
Ja, nee, aber deshalb können wir es vielleicht beide nicht aufmachen.
Na gut. Wird schon klappen.
Ich frage mal schon Sophia, ob es geht.
Mhm. Schönen Gruß. Everybody, shall we start? We were hoping to transmit a live stream for those participants who are absent. But last time, after about an hour, it broke down for reasons I don't know. And I'm not sure whether it's running now. I do hope it is. All right, now, on the web page of this lecture, some things have changed. So, for example, you now find a link with a video from last time, and I'm at least planning to add videos for every lecture we have. And perhaps most importantly, there's a problem sheet. I'm sure you have been waiting for it. The idea is that you go through this problem sheet and you discuss the problems next week in the first tutorial group. And I'm not sure yet how we will grade the lecture at the end, or how we will measure the success, your success in this lecture at the end. This could be an exam, which could either be written or orally. Just for my information, could you lift your hand if you need the points and the grade? All right. Yes. We need to measure we need to measure somehow whether you participated successfully. So do you need the points? Who does? All right. There will be an exam. Let's see how. Yeah. Then I can't fix it right now. I'm sorry. All right. So, do you have any questions concerning the organization of the lecture and of the tutorials? Yeah. Celine Üstender, who is going to be the tutor, will send around a mail to you, to all of you who are registered here, in order to find out what the best time would be, and she's arranging to find a lecture hall for that, depending on how many of you will respond. Next week. Yeah, Robin?
So, within an exam, do we have only to participate in the lecture, or do we also have to be well prepared? Or?
Well, as always, you know, you're a grown man, and it's your business, but I recommend at least following the problem sheets. Okay. Anything else concerning the organization? this is not the case, then we move on with the wrong button. We move on with the lecture. So the key points of last time were that, first of all, we went through the foundations of the cosmological standard model. And then say hi from me. And then we discussed the usual approach to cosmic structure formation. And in the first part, I introduced the assumptions that underlie the cosmological standard model. That is, we assume that general relativity is the correct theory of gravity for doing that, and that we can make certain symmetry assumptions on the space-time that general relativity is operating on. And these assumptions were, number one, the universe is on average isotropic around us. Number two, the same holds for everybody else in the universe. And this simplifies the form of the metric considerably. Then we can apply the Einstein field equations to the metric, and we find the two Friedmann equations, of which I showed you that you can combine them to retain one of these equations plus an energy conservation equation. And I told you that this is no surprise, because by construction, by the so-called second contracted Bianchi identity, Einstein's field equations are constructed such as to satisfy local energy momentum conservation. So far, so good. Then I introduced the Euler-Poisson system, a system of three equations. Two of them are conservation equations, namely the equation of mass conservation, the equation of momentum conservation, and the third one is the Poisson equation for the gravitational field. And we were about to perturb them and to linearize them and to see what we can conclude from them after we had transported them to co-moving coordinates. Now, after linearization, the continuity equation looked like this. I'm going to leave out the vector arrows. Delta dot, delta was the density contrast, so the deviation of the density from its mean value. U was the peculiar velocity, that is the velocity of any particle in the cosmos relative to the Hubble expansion, relative to the Hubble flow. So the motion of particles, which is only due to space-time expansion, is already taken out, and U is the peculiar velocity of the motion relative to the Hubble velocity. That was the first equation, and I told you, first of all, this is going to be most important later, and it formulates something that you would naively expect, right? Wherever the density is locally growing, matter must be flowing together, which means that you need to have a converging flow there. This is the simple statement of that equation. But we had another equation too, and that was the Euler equation, which I'm going to write in full glory first, leaving out pressure gradients. So usually you would have pressure gradient forces. We are neglecting pressure here because we are dealing with dark matter. So I'm leaving out a term which would read minus gradient pressure divided by density. And then this is the equation of momentum conservation. This is a total time derivative of the velocity field. So what you see here is just Newton's second law. And acceleration is force. All right. Now we are going to introduce, first of all, co-moving coordinates, which means that we have to replace the dtv here by dtv minus h q times gradient v. Remember, this was necessary because taking a partial time derivative keeping co-moving coordinates constant is different from taking a partial time derivative while keeping physical coordinates constant. And so this was the reason for this term to appear. Then in co-moving coordinates, the gradient just needs to be replaced by 1 over scale factor times the gradient, and we have the same over here. So now we are in co-moving coordinates, and the gradients operate on co-moving coordinates now, and the time derivative is adapted to that. Now I'm going to insert, like last time, the perturbation ansatz. Right? I say the velocity is the Hubble velocity. That's the velocity of the unperturbed background. So of any particles moving together with the background, and then I have scale factor times the peculiar velocity with respect or relative to this background motion. All right. This is just an exercise in writing things down. Remember last time I dropped all gradients acting on the mean density. This is because, of course, the mean density is constant. I can't do this here because the mean velocity is not constant with space, right? Because it's Hubble's law. As you move away, the velocity is going to increase, so I have to retain the gradients on the Hubble velocity as well. All right, that's that. Then we have 1 over a velocity times gradient acting on Hubble velocity plus peculiar velocity. And on the right-hand side, we have the same as we had. Now I'm using the same argument as last time. I'm using the argument that this equation must separately hold also in absence of perturbation. So if I set u equal to 0, the same equation must hold, acting only on the Hubble velocity. So at the same time, we must have dTVH minus hq times nabla vh plus 1 over a vh times nabla vh is is 0. Because in absence of perturbations, we do not have a perturbing gravitational potential either. So this is the equation that holds on the background separately for the Hubble velocity alone. And this is the equation that holds together with the perturbation. And both of them must be satisfied. And so you see, if you subtract the second from this one from that one, then this term drops out. This term drops out. The term containing VH times nabla VH drops out. And the right-hand side remains. All right, so taking these two together means dt acting on AU minus HQ times nabla AU. Now here, of course, the nabla does not act on A, so I could pull the A out. I'm going to do so later. Then I have 1 over A VH times nabla acting on AU only. That's the first mixed term that we retain. Then the next one is U times nabla acting on VH, the second mixed term. And then I have a third mixed term, which is nonlinear in the velocities, which contains two factors of the peculiar velocity. All right, and the right-hand side remains, that's minus nabla phi over A. Now we can further simplify things. First of all, I can pull this A from underneath the gradient out, and I can cancel the 1 over A here. Then I can insert what I know of the Hubble velocity, namely that it is A dot times Q. And then you come to this term here, which has a negative sign instead of a positive one. There's the Hubble function. This is A dot over A. I can pull the A out. Then I have minus A dot Q times nabla applied to U, and I have the same term positive. They cancel. So this one cancels this one. Now this is going to be perhaps surprising. What is this? It's the vector U times the vector nabla. So this ux dx plus uy dy plus uz dz. And this acts on A times Q. So what we have is ux times dx applied to x. And nothing else, because the first component of VH only contains x. Then I have uy times dy applied to y, and uz times dz applied to z. So this differential operator applied to VH just gives 1 for every component. So u times nabla applied to VH is just A dot times u. Okay, and now in symbols. So we have u times nabla applied to A dot q. Okay, this q is a vector. So this is, let me write this out, ux dx plus uy dy plus uz dz. The same thing as this. Now I have A dot x, y, z. Right? This is the vector q. And now you see what I just described in words, right? You apply this differential operator to x. dy doesn't act, dz doesn't act, only dx acts, gives you a 1. Same for all the others. Right, so you get ux, uy, uz. So this means that this is A dot times u. Look, there's another term, A dot times u, coming from here later. All right, what else? Well, I can't do much about this one. That's the nonlinear term that gives rise to nonlinearities in hydrodynamics all the way long. But this is going to die anyway because we are going to linearize the equations. Nonetheless, if I summarize, I get an A dot u from here, and I get an A dot u from here, and I get another u dot a from here. So let me write a u dot plus 2 times A dot u. Now I have these two terms and that one together. Those cancel anyway. Then I have plus A u times nabla applied to u equals minus nabla phi divided by A. Okay, wonderful. Now I just divide by A and I'm done. So this means that we have u dot plus 2h u. And if I divide by A, I get the Hubble function. This A drops out, just leaves me u times nabla applied to u. And on the right-hand side, I'm getting minus nabla phi divided by A squared. No approximation so far. Now I'm approximating. Now I'm linearizing this equation. In other words, I'm dropping the term which is quadratic in the perturbation, which is u times nabla times u. So the linear equation, let me write this upstairs here. The linear equation for the velocity is u dot plus 2 times h times u equals minus grad phi divided by A squared. Okay. One moment. These are linearized continuity and Euler equations. And now I still need the Poisson equation, which looks like this. Right, we introduced this last time. I told you that the fact that here is only the density fluctuation appearing, not the complete density, is a reflection of the so-called Jean swindle, which is necessary because we are applying Newtonian theory of gravity to a system it wasn't made for, namely to an infinitely extended system. And this factor of a squared comes because we have transformed this Laplacian to co-moving coordinates. Now,
why are we able to linearize this equation?
Because we want to have linear perturbation theory. Did you say why we are able to do this, or why we are doing this?
Why we're able to do this?
Because we assume that perturbations are small. So we know from observations of the cosmic microwave background, for example, the density fluctuations in the early universe have been small. If density fluctuations have been small, velocity perturbations also have to have been small, which means that at least for some time, to be quantified, in the early universe, the linear approximation is in order. Yes?
That's really, that for some time is really an important qualifier, because even if the perturbation stays small, the perturbative approach might still be sectional, right? So
Absolutely. Absolutely, we see about that. All right. Yes. Don't tell the university administration. Fortunately, it's warm outside. All right, nonetheless, this is the goal we had for the moment, right? We wanted to have perturbation equations for density fluctuations. And of course, we have to take into account that where you perturb the density, you also have to perturb the motion of the matter. So at the same time, you have to perturb the velocity field. And then we have a linear system of equations. Now we are going to combine these equations into one. And this is an equation that is going to be very important for moving on. So the usual trick for combining these equations is you take the time derivative of the first and the divergence of the second. Then in both of them you have the divergence of u dot, and then you eliminate u dot between the two. Like this, you see, you take a second time derivative. Of the next equation, you take the divergence. You now get the Laplacian of the potential, fortunately, because we know from the Poisson equation what that is. Conveniently, the a square cancels. And we know how the right-hand side relates to the density, or rather the density fluctuations. Now we have to take into account that we also know the divergence of u from the continuity equation. Right? We know that divergence of u is minus delta dot. And so if we now combine these two equations by eliminating the divergence of u dot in between the two, we get one equation for the density contrast out. Right? So I subtract the second from the first. I'm using this minus sign here to get delta double dot plus 2h delta dot equals 4 pi g rho bar delta. This is the linear growth equation for density fluctuations, a very important equation that occurs everywhere in cosmology. And I wanted to show in detail how this comes about. Now we need to think a little bit more about this. First of all, I can use the definition of the critical density, the critical cosmic density that we introduced last time, in order to simplify the right-hand side of this equation. And for this, I'm going to write 4 pi g times rho bar is 8 pi g divided by 3h squared. Now it's wrong, of course. So I have to fix this. Times rho bar. And now you see, this is the critical density at any point in time during the cosmic evolution. Last time we introduced this as 8 pi g divided by 3h0 squared. That would be the critical density today. 8 pi g divided by 3h squared, that is the critical density at any point in time. So here you multiply, the inverse of that I should say, you multiply rho bar by the inverse critical density, that's the omega matter parameter. So I can simply write this as 3h squared divided by 2 omega matter. And this is not omega matter today, this is not omega matter 0, but it's omega matter, right? The density parameter, that is the density expressed in terms of the critical density. So that's the critical density at any point in time. Now, of course, you can also write this, you can also refer this to the critical density today. And since you very often find this as well, let me write this underneath. All right, I'm starting here again, and now I'm going to write 8 pi g divided by 3h0 squared. Now, of course, I have to cancel that. Then I have rho bar again. But as we saw last time, rho bar is rho bar 0, the mean density today, times scale factor of the minus third power. Now I can combine rho 0 bar together with 8 pi g divided by 3h0 squared to get omega m0. So this would be 3 over 2 times h0 squared times omega m0 times 8 to the minus 3. Both, of course, are completely equivalent. It's just a matter of what you find more convenient, either expressing the right-hand side in terms of a time-dependent density parameter or in terms of a time-independent density parameter referred to some reference point in time, for example, today. But then you have to adapt this a little bit. All right. Mixed forms are also possible. Right? Okay. Let me stick to the first expression here. And write delta double dot plus 2h times delta equals 3 over 2 h squared omega m times delta. Is that a problem?
A little bit confusing, because in the upper equation you have 3h squared over half times omega m. And in the bottom one you have the h0 squared. But omega m itself is omega m0 times 8 to the minus 3, so why is the h1 without the 0 and 1 with?
Do you trust me up to here? This is omega m0. Then the rest follows.
Yes, we were just wondering how to get to the upper equation.
Okay. We are going to need this anyway, then, yeah, Philip.
Shouldn't it be minus 4 pi g rho bar delta? Because in the concept higher
Of course, of course. Now, wait a moment. This is negative. And then you subtract this equation from that one, so you get a plus sign. And that's important. That's important for the following reason. No, let's fix the omegas first. Now, for you, Alex. Let me show it nonetheless, because we need that anyway. So I'm writing omega m now, the density parameter at any point in time. This is 8 pi g divided by 3h squared times the mean density. That is its definition. Now I'm writing 8 pi g divided by 3h0 squared times h0 squared divided by h squared times rho bar 0 times a to the minus 3. Okay? Now I can combine again 8 pi g divided by 3h0 squared times rho 0 bar to omega m0. Now instead of h0 squared over h squared, I'm writing this, the expansion function e squared. This is going to enter later again. Remember, right, we said the Hubble function h is the Hubble constant times the expansion function. So h0 squared divided by h squared is just 1 over e squared, and then I have a cubed. This is a lovely expression. Remember, we had e squared is omega m0 divided by a cubed plus omega lambda 0. This was the expansion function in at least the matter-dominated lambda CDM cosmology, standard cosmology. A cubed times e squared in this particular cosmology is a cube, no, omega m. Getting smaller as I'm going back in time. Sorry, back in time is this direction. This term is going to disappear, and then the density parameter omega m is going to approach unity rather quickly. That's important. We are going to need this later. Okay. So whatever the value of omega m0 may be, it's right. So let me return to this equation. Suppose this term was not there. Then you have an oscillator equation, right? You have an equation that has a second time derivative of some quantity that is proportional to the quantity itself. It's an oscillator equation. However, with a negative frequency squared. So it's an oscillator equation with an imaginary frequency. Then of course it has exponential, well, has exponential solutions which contain e to the plus or minus I times the frequency, but the frequency is an imaginary number. So without this term here, you would get exponentially growing or exponentially decaying solutions. Okay, you would just get, instead of the trigonometric functions that solve the oscillator equation, you would get exponential functions. So the hyperbolic sine and the hyperbolic cosine instead of the sine or the cosine. All right. Why is that? You see gravitational instability there. Right? You get positive density fluctuations growing, you get negative density fluctuations shrinking. All right. But then the expansion term here, this corresponds to a friction term in the harmonic oscillator. And this slows down the exponential growth. to something smaller. Right? So exponential growth that you would expect from the gravitational instability is slowed down by the expansion of the background spacetime. This is also called the Hubble drag. Right? Friction corresponds to a friction term in the harmonic oscillator. It's a friction term introduced by background expansion. This means that any growth of structures needs to compensate against the expansion of spacetime. Right? Anything that needs to grow in competition with spatial expansion is slowed down by spatial expansion. All right, so let's look a little bit further into that. But it is very convenient before to change the independent variable entering into this equation, namely from time to the scale factor itself. Right? A recurring pattern in what we are doing here is that we choose appropriate time coordinates. And of course, we can do that as long as the mapping between our old time coordinate and our new time coordinate is strictly monotonic. If that would not be the case, would not be a good choice, but anyway. All right, so I want to replace time by the scale factor as an independent coordinate, and I'm doing it like this. So I'm replacing dt by dA times A dot. Right? Okay. I'm writing this as AH times dA. That's the same thing by the definition of the Hubble function. Now I'm going to take the second time derivative. This is now AH dA applied to AH dA. AH. Now, okay, if I'm pulling the dA through to that scale factor derivative here, I'm just getting a dA squared, fine. But then on the way, I will also have to apply to the AH. And this is going to be this factor AH from here. Now, this derived with respect to A is H plus A times H prime. And the dA remains, okay? It looks a bit weird, right? I'm purposefully writing it like this. And if you intend to solve the problem sheet, you will need this again. So now I can pull AH squared out of both terms, and I get 1 over A plus H prime over H times dA. That's the second derivative. Now I just, second time derivative. Now I just insert this into the growth equation. All right, now what do you see? We have to replace delta double dot by this operator applied to delta. And here get a 1 over A times dA applied to delta. But then we have another term, 2 times H times delta dot. And the delta dot contains this term here. But we have pulled AH square out. So if I pull AH square out of this term, 2H times the time derivative, I'm getting another 2 of those here. All right, let's see that. So now I'm writing the derivative with respect to the scale factor as a prime. So then from this expression here, I'm getting a double prime. Then I have 1 over a plus, now let me write h prime over h as e prime over e. Right, by definition of the expansion function, delta prime. This times this factor ah squared is just delta double dot. Now we move on. This is 2 times h times a single time derivative. So multiplied with ah squared. The whole equation by ah squared. So only this remains. But this is of the same form as this one. So in total we get 1 over a plus 2 over a is 3 over a times delta prime. So that simplifies quite considerably. And on the right hand side I have 3 over 2 h squared omega m times delta. Okay, fine. So this is delta double prime plus 3 over a plus e prime over e delta prime equals 3 over 2. Wait a moment. We have divided by a h squared. So I need to fix it like this. So this is omega m divided by a squared times delta. All right. Let's play a little further. It's going to be instructive. I'm inserting now on both sides the expressions for the matter density parameter as a function of time and for the expansion function. We've seen that in the standard cosmological model, E squared is omega m0 divided by a cubed plus omega lambda 0. I get 2e prime on the left-hand side. On the right-hand side, I get minus 3 omega m0 divided by a to the 4th. Aha. So this means that e prime over e is just this expression divided by 2e squared. So that's going to be minus 3 halves omega m0 divided by a to the 4th times the expansion function squared. So this is a times omega m0 plus a cubed times omega lambda 0. And now you see, all right, if I go to the early universe, right, where a is small, this just turns into a factor 1. And the whole expression goes into minus 3 over 2a. And this term just retains 3 over 2a. And we are going to use that, of course. And it's a very simple expression that is valid at early times, irrespective of the precise cosmological parameters. Same on the right-hand side. Here I'm using what we said before, that omega m is omega m0 divided by omega m0 in the universe. In the right-hand side, the omega m also changes just to a factor of 1. And then the equation becomes very simple. So irrespective of the present cosmological parameters, at small scale factor, this becomes delta double prime plus 3 over 2a times delta prime equals 3 over 2a squared times delta. That's important. So this is now the approximation of the linear growth equation at early times. Now suppose you make an ansatz for delta as a power law. We know it can't be exponential anymore, right? Because it would be exponential if the friction term was absent. But there is a friction term, so let's try a power law. Now suppose you start with a power law. Let's say delta is delta 0 times the scale factor raised to some power n.